years ago, when we were planning what turned out to be the last visit day colloquium before we went to COVID, Alex said, you know, we're not going to be able to ask you to give a CAM colloquium on visit day for a number of years, so why don't you do it today, or why don't you do it this year? And I did. And I'm very pleased to be able to return the favor this year and ask Alex to give the visit day colloquium. I've known Alex since I came here, and actually a little bit before. We overlapped at Berkeley, though we didn't really know each other then. And Alex and I have been co-conspirators on the scientific computing seminar and on various other things for a long time. And this past year, just finally, for the first time, wrote a paper together. And today, I'm very interested to hear him talk about you know, various things in game theory. And with that, I'll hand it off to him.
Thank you so much. I'll try to be loud. Usually it's not a problem, but I spoke for a long time today, so if I'm getting too quiet, please tell me. I'll try to speak up more. One of my colleagues met me in the corridor in the math department and said, I hear you're talking about things you know nothing about. I said, that's right, that's the most fun. So let's see if we can make sense of it together. It's a great pleasure to give a visit day colloquium talk. I'm both honored and excited. And this talk works the best, I think, because it all started for me, my personal immersion into this territory, started with another CAM colloquium about 4 years ago, given by Jake Scott, who is an oncologist in Cleveland Clinic and who also has a PhD in applied mathematics from Oxford University. Every visit day talk, I think we have a tradition in the making, should probably have some moral to it. Alex Townsend's was you should hang out with interesting people and go dining together to nice places, because his collaboration started that way. My moral today is you should go to colloquiums and seminars and listen to people, and you never know when the inspiration might strike you. Okay. Without further ado, oh yeah, and I should say that aside from Jake Scott, this is also a collaboration with two CAMsters, CAM graduate students, Mark Guzman and Mingyi Wang. I saw Mingyi in the audience. Is Mark here as well? Probably not. Okay, I can say anything I want about Mark. Good. So the story starts also in the year which I remember well, 1973. I was born then. It started with two engineers. I think one was the aviation engineer, the other chemical engineer, who decided to work on biology and revolutionized one of the areas of biology, mathematical biology. John Maynard Smith and George Price wrote this paper, from which what is known today as evolutionary game theory started. And among other questions, they were trying to answer the question of why don't animals fight to death more often? It seems like a good thing to do. If you're stronger than your opponent, just get rid of them. Right? The more resources to you after that, you produce more offspring, why not? And why do so many different species have ritualized fights? So you see that in king cobras, you see this with cats who are screaming at each other instead of fighting really badly. You see this with elks and with deer, where they walk side by side for a long time before they start the real fight, and sometimes don't. Why does it happen? Let me start with this very simple example, which is a game of hypothetical hawks and hypothetical doves. So, not real hawks and real doves, but basically hawks are the ones who enjoy the fight and are not shying away from it, and doves are the ones who are peaceful. In here in this matrix, I'm providing the payoff for the column players. So this is whose payoffs we're seeing. This is for the hawks. And the column headers give you who are they playing against when they get that payoff. Okay? It's a symmetric game. And there are two things, two constants which matter here. V is the resource value. This is the resource which they are trying to split or share or somehow decide who gets it. And C is the possible cost of a serious fight. So hawks always are willing to fight. And doves are, if two doves are facing each other, they split the resource without fighting. Each one of them gets half of it. On the other hand, when dove faces a hawk, dove gets nothing because the dove is not interested in a fight, and hawk gets everything. On the other hand, when two hawks get together, well, each one of them ends up with half of the resources, but they also pay the price of the fight, right? So this is the setting, and it's very easy to see that when value of the resources is strictly bigger than the cost of the fight, the only stable thing to do, the only advantageous thing to do is to always be a hawk. You can prove this quite easily. And this is called the evolutionary stable strategy. This is additional condition on top of being the Nash equilibrium. I don't want to go into this one right now. I'm going to keep it on an intuitive level for now. But if the value of the resources is lesser than the cost of the fight, then you might actually have both populations existing at an equilibrium with each other. This would be called the coexistence equilibrium. Let's figure out the likely payoff, the expected payoff to both of them. Suppose Q is the proportion of the population which are hawks. Then for the hawk, if they face another hawk, they get V minus C over 2. If they are lucky and they got to be against the dove, they get the loot without paying anything for it. For the dove, only when they are facing another dove, they get half of the resources. At the equilibrium, those two things should be equal. There should be no advantage for one of them versus the other. And so when you set those two things equal, you immediately see that Q has to be equal to V over C. Okay. That tells you that when the price of fighting, the cost of fighting goes up, you will see a smaller proportion of hawks in the population. So the animals which are really capable of inflicting bad damage on each other will be less likely to fight over the resources. They would engage in ritualized fighting behavior instead. Okay, so that's a lovely start which they had. Interestingly, so how is this different from regular game theory? In regular game theory, you are rationally deciding which one of the strategies available to you you want to play. Here, we're assuming that it's inherited. They're not really making a conscious choice. They're behaving the way they are. They're either hawks or doves. But those who get higher payoffs have a higher chance of producing offspring and over the time start to dominate. That's the mechanism. On the other hand, with non-inherited traits, sometimes you can use similar analysis as well. And my next example is the public goods game. Do you mind contributing more than others? So we can make it a story of a group project for the students. Some students in the group are producers in the population of students, and they will be working hard on the project. And the others are defectors who will be free riding and just trying to get a good grade without putting any time in. Here are the payoffs for them. First of all, if you got two free riders together, there is nothing produced, and both of them are getting 0. If you have, so there is a public value of the product, and that public product is shared. Whatever was produced is shared among all the participants, whether or not they have completed it. So if you have two producers, both of them are producing value V, and both of them are paying personal cost of producing C. If, on the other hand, you have a producer which is paired with a defector, producer is getting half of the value, but pays the entire cost of production. And the defector just gets the value for free, half of the value produced for free. The setting is clear? Okay. Let's do the same kind of analysis. If Q is a fraction of players of type P, producers, you can write out those payoffs which they're having here and compare them, and you discover that this Q times V over 2 is in both places, but the producer will have an additional term of V over 2 minus C. So if this is positive, producer actually has better returns, and it's better to be a producer, right? And that will be the stable equilibrium. Everything will be tending to that. So it's counterintuitive, right? It's counterintuitive because you think, well, if I'm a defector, on occasion I get a good grade without putting in any work. But on the other hand, if I am paired with another defector, I'm going to get 0. So that really gets to me, and even if the population is mainly producers, whenever producer happens to be paired with another producer, they both generate value V, and they both end up with V minus. So whenever this quantity is bigger than 0, producers win, and the equilibrium, the stable equilibrium is there. Similarly, you can pose a game of n+1 players. What does it mean? There is a huge population, and at random, uniformly at random, blocking n+1 participants from that population, and then forcing them to produce values or not produce values, depending on whether or not they are producers or defectors. Whatever they produce is split over all of the n+1 participants. Okay? So in this case, the condition for producers to win is V over n+1 minus C has to be positive. I'll note that most of us are not this way. We're animals which are not quite rational. We have an acute sense of fairness, and most of us are not willing to rationally behave this way if we feel that there are too many freeloaders around us. So, but I guess if I am enjoying my group project so much that I don't care whether or not anybody else is doing it, that even the n+1 part of the credit is already a value bigger than my time which I put into it, I will still be doing it. Okay. All of this was about the equilibrium. But now I would like to talk about things changing in time. Right? What if you start not in equilibrium? How do you get there? Are there multiple equilibria to which you could get, etc.? So in order to do that, I would like to derive ordinary differential equations. And let me start with the statement that I have m different strategies. So that would be m different types of behavior, for example, or m different types of animals which are competing for resources. And Z sub I is the abundance of the Ive strategy. So how many animals of that type, of the Ive type, do I have in the population? Z is just the sum of all of them. That's the full population size. It will be changing as a function of time. Now, I will not be focusing on those Z sub I's though. I will be instead focusing on X sub I's, the relative abundance. What proportion of population belongs to the type I? And so this is Z sub I divided by Z. And I will say that the fitness of the Ive strategy depends on the full composition of the current composition of the population. And this one is the iffiest of my assumptions, because notice that the dependence is not on the current population size or on the ZIs, but only on the relative frequency of different strategies. Okay. It also is handy to introduce the population averaged fitness. So this is what it sounds like. You take all of those F sub I's and you average them with the weight being the current proportion of population of type I. You put this together. So first of all, the natural for the animals, the natural ODE, which describes how their abundance, absolute abundance, is changing as a function of time, is the current number of animals times their fitness. So think of it as proportional to the rate of procreation, of how many offspring they produce to survive. You can also add them all up to get the growth of the full population. And what you get is that a similar equation where Z is multiplied by, not surprisingly, population averaged fitness. Okay? Now, but I'm interested in those exabytes instead. Exabyte is equal to Z sub I divided by Z. I have ODEs for the derivatives of each one of them, so I can use what is it, quotient rule, or product rule, whichever, and get the ODE for exabytes. So that ODE is known as the replicator equation. This is the basic building tool of evolutionary game theory, developed in 1978. And by using the quotient rule, I can derive these two. I would derive, I guess, this form of it, and it's easy to rewrite it in that one. They both have their own advantages. The first form tells me that the frequency of strategy I is growing proportionally to by how much its fitness is bigger than the population average fitness. Okay? So that's a very natural biological interpretation. But it's much trickier for me to talk about the change in exabytes when I'm talking about the group of humans. I'm not thinking of humans who are doing well, putting honest efforts in their group projects, producing more offspring, for better or for worse. That's not the relationship we're talking about. Instead, what I'm thinking of is we are mimicking other players from time to time. So what is, and it's easy to make a transition from this one to that one. You just remember the definition of f, and you split f sub I as f sub I times the sum of xj's. That's the whole transition. Nothing fancy. But what this says is every now and then, players of type xi and xj come together, and they compare their scorecards. Who is doing better and who is doing worse. And the player who has the lower scorecard, lower fitness, is likely to switch with some probability to the strategy of the better player. And how likely is proportional to by how much the strategy of the other player is better. So you're thinking of two different time scales. On one time scale, they're very rapidly playing many games with completely at random selected participants from the full population. On a slower time scale, every now and then, two people come together and compare how well they're doing right now. And if one of them is doing significantly better, there is a likely split in the behavior of the other. Is this model clear? Okay. Notice that all of the exabytes add up to 1. And that means that when I will be talking about the phase portraits of those ODEs, it will not be m-dimensional. Instead, I can do m-1 dimensional. I can keep track of just the first m-1 of them, and the other one is computed from this. Okay. What's the connection to the two-player games? Where do those f sub i's, fitness functions, come from? Well, one way in which, to which I alluded already, is f sub i's come from playing many games with people randomly selected from the population. So if x is the vector of the current composition of the population, of the relative abundances of all subtypes, I can describe the f sub I, the fitness of the I type, using the product of the matrix A of the payoffs in that original matrix, for example, which I had here, right? So this is my matrix A. So taking the product of A with X will give me the payoffs, vector of payoffs for all strategies. Take the ith element of it, and you got the f sub I. If you want to population average, it becomes this quadratic form here. Okay? Things become a little more complicated if you have games of n plus 1 players, right? More than 2 players. but you can do similar things. Okay, having just two strategies is kind of boring, so let's make things a little interesting. Let's talk about the everybody's favorite game with three strategies, the rock, paper, scissors game. So please ignore the deltas for now. Is it clear that the payoffs which are written in here, they're the payoffs for the column player in here? Does that ring a bell? Looks like your rock, paper, scissors from your childhood. Yeah? Okay, so I could treat this as my matrix A, and I could come up with the fitness functions based on it, based on this matrix A, and solve that system of ODEs. And the next slide shows the phase portrait. So let's ignore this picture for now and focus on the one on the left. This is the phase portrait in reduced coordinates. I'm only showing you the total proportion of the rock players on the horizontal axis and total proportion of the paper players on the vertical axis. Right? So it's sort of a shadow into x1, x2 plane of the triangle x1, x2, x3. Right? So for example, when we're on this edge, there are no scissors players. When we are at this point, everyone is playing rocks. Here, everyone is playing paper, and here, everyone is playing scissors. Clear? Naturally, those three are equilibria of my dynamical systems because I'm not considering any mutations. There is no spontaneous switching. If I'm changing, comparing my strategy to somebody else, if they're all playing the same thing I am, even if I switch, I stay the same. But there is this coexistence equilibrium, which corresponds to exactly 1/3 of people playing rock, 1/3 playing scissors, 1/3 playing paper. The rest of the trajectories are periodic orbits. So that means that you are going to have cyclic oscillations. You will have cyclic oscillations in what type of player you will see more in the game. And it makes sense. If more people are starting to play rock, then the fitness of the paper players dramatically grows. They win more often. So as a result, the trajectory leads us to a higher number of paper players. Once you've got so many paper players, it's really nice to play scissors, so people switch here, etc., rinse and repeat. Right? Now, let me change hats for a second and say, I don't want to be just a player. I want to be the guy who sets the rules. And maybe I have some system-wide goals. Maybe the system is very inefficient when they're oscillating that far from an equilibrium, coexistence equilibrium. Maybe I want them closer. One way I can entice this, I could pay the subsidies. I could say, you know what, whenever you pay rock, paper, if you won against a rock, I'm actually going to throw in delta more dollars out of my pocket. Ditto for the other winners. So delta is my opportunity to control the system. If I use positive delta, the phase portrait changes and everything spirals in towards the equilibrium. And it becomes a stable sink, yes? And so presumably I could get the trajectory close enough, then stop paying subsidies, switch to this world, and oscillate, continue walking around the trajectory, which is much closer to the equilibrium. A question which I was interested in with Mark Guzman was, what's the best way of doing it? Should we be paying the subsidies all the time? Maybe there are only some parts of the domain of this composition where we should be offering that incentive. Should we be offering more incentive for some types of players only rather than the others? And so we were hoping to see some applications of it in social sciences or economics, but everything we were looking at was pretty contrived. It is an optimal control problem. How do you write social engineering? How do you make the society be the way it should be in your dreams? Turns out that in nature, you have rock, paper, scissors dynamics as well. One of the most well-known examples is the example of side-blotched lizards. And by the way, John Maynard Smith hypothesized that there should be rock, paper, scissors dynamics in nature, but he didn't have any examples, so they came much later. You have a question?
Yeah, I'm curious, what happens if we try and sort of like disincentivize the strategy, if we make delta negative? How does that change?
It will spiral out, good question.
Okay.
It will become a source.
Okay.
Yeah. So it turns out there is this really weird species of lizards which have 3 different morphs for their male lizards of that time. Morphs are not subspecies, but something like subspecies. Those are inherited phenotypes and different types of behavior. There are yellow morphs, blue ones. It doesn't come out as blue on the screen for some reason. And the orange ones, and that's barely orange. But believe me, it is. They have surprisingly different strategies in life. The blue ones, they're territorial. They're very defensive. They mate only with one female, and they stay with that female and guard it. The orange ones are bigger and more aggressive, and they try to conquer much bigger territory and have many, many different females. So if you take a blue-dominated territory, in which blue are more common, and you drop an orange one into that territory, it will produce a lot more offspring than blue does. Okay? So here I'm showing who is in the majority, who is common. And here I'm showing who will be winning. Right? So it would be a boring story about hawks and doves, perhaps, except that there is also yellow, and yellow is very sneaky. Yellow does not control any territory. Instead, it sneaks through others' territories and mates with the females which are supposedly controlled by those other lizards. It doesn't have much success against blue because blue does not control that much of a territory. So here the success of yellow is very small. But against orange it does surprisingly well because orange is trying to conquer a huge territory and cannot defend all of it. And it's really sneaky because when orange approaches it, it actually pretends to be a female. So there are rarely fights, direct fights. On the other hand, yellow loses against blue. If you drop blue into the yellow territory, blue will win because as a fighter they're better. So you got this cyclic, non-transitive dominance, non-transitive relationship, and cyclic relationship for the dominance. And scientists decided to measure whether or not the population, the fraction of the population will be changing like in those periodic orbits I showed you. And it comes pretty darn close. I mean, think about it. Those are experimental measurements with somebody counting the lizards in the desert. This is as convincing as experimental evidence in ecology gets, if you like. Okay. So, that was interesting. I knew about this example. But then Jake Scott came and gave this colloquium in camp and told us this story about 3 types of cancer cells. Some tumors. Now, here comes the disclaimer. I am talking about stuff I know little about. I am not a biologist. I'm not an oncologist. I have read a number of those papers, but those are highly idealized models. And so, for example, asking me what kind of cancer it is, yeah, I can tell you a little bit about it, but the general is so idealized that it does not matter. But the general mechanism is pretty, applies across several categories of tumors. So you have 3 types of cells here. The GLY cells are glycolytic. They produce acid. They don't need oxygen. They produce acid as the side effect of their getting the energy. That's their mechanism, chemical mechanism of producing the energy. In order to get oxygen, you need vasculature. One of the signals for the body to produce vasculature is the signal protein called VEGF. So there are types of cancer cells which produce more of this VEGF to encourage the production of the vasculature, enhancement of the vasculature. As a result, they get more oxygen. And these two types of cells, VOP and DEF, they are aerobic. They manage to get the energy using the oxygen. So for them, it's a huge benefit. Okay? Except that in addition to VOP who are benefiting from oxygen and paying the price to produce it, there are also DEF defector cells or free riders which enjoy oxygen, get advantages from it, but are not producing that protein. Not spending any energy on this. This is related to the public goods game, which I showed you before. So we will have to pretend to be cancer cells and take their perspective for a second. Because for them, the acid here is a public good. It doesn't hurt them, but it does hurt healthy tissue around them. On the other hand, the vasculature is a club good. It's enjoyed only by some of the players, but not all. Clear? There is a way to write down the ODE model based on the interaction of n+1 cells. This is why I wanted to go beyond two-player games. So the idea is you do not model directly the spatial composition of the tumor, but you keep track of the proportion of cells of each type in the tumor. And now you assume that it's all well mixed somehow. And that same proportion is everywhere. And so you decide what are the n neighbors of the current cell at random. You pick them at random from the general population based on the current frequency of each one of those. And you decide how much acid is produced, how much VEGF is produced, and what's the payout for each one of the three strategies. Is this idea clear? Okay. So Jake came and gave us a talk here, which I found to be very inspiring, about the dynamics based on this simple model. And depending on the relationship between the number of cells, the cost of producing VEGF, the benefit from vasculature, and the benefit from acid, depending on how all those things are related to each other, the phase portraits can be quite different. In one of them, on which I will be basing most of what I tell you in the rest of the lecture, you see the same rock, paper, scissors type dynamics. There is a coexistence equilibrium and a cyclic pattern. So if you don't treat with any drugs, the proportion of the cells are oscillating periodically. So this is the story which you see up top here. So Jim told us about the therapy where you're trying to get rid of the GLY cells. There is some drug which affects only them. You're trying to decide when to apply that drug or whether to apply it. The top picture is you're not hitting it with drugs at all. You see nice periodic motion for all three. The next one is a poorly timed treatment. You just start, this is this gray rectangle, this is the period where you hit it with drugs. You see that green goes down dramatically, but then you stop administering drugs and it rebounds and actually comes even higher than it would have been otherwise, and the patient dies. Right? And finally, if you wait a bit and apply it, you let the natural dynamics of the competition to bring green down until you start hitting it with the drugs here, you actually manage to get it to a very, very low level from which it doesn't recover. Yes, please.
Just to make sure I'm clear, you think of the y-axis as the representative proportion of
Yes.
the cancer cells in your entire body, or is it with respect to local region?
So in that tumor, so I'm not localizing. There is no spatial structure which is modeled in here. On the other hand, you are locally interacting only with n neighbors, but those neighbors are drawn uniformly at random from the current distribution of cells of different types.
And then just to make sure I'm clear, those neighbors will be healthy, we would assume that they're healthy. In other words,
There are no healthy things here at all. All three of them are cancer cells.
okay.
but we're trying to eradicate only one type, because possibly we have other therapies to get rid of the others later. Yes, please.
What's the time scale we're talking about here?
30.
What is the time scale?
I know, 30 units. So Xingyin, an excellent question, but remember my warning that this is a highly idealized model. The time scales on which the oscillations like that do happen in real tumors and real patients, I do not know the answer. They do happen. There isn't, as far as I know, a proof so far, experimental proof, that that kind of dynamics is actually observed in cancers. It has been observed in many other biological systems, including in coral reefs, corals in the reef, including in several types of grass and parasitic grasses, and including in E. coli bacteria. So there are papers I can provide which experimentally have determined that this actually happens not just in the lizards. One of the ongoing projects is to figure out whether or not there is confirmation for different types of face portraits in real biological lab. Okay, so this is my long answer to the question to which I don't have a short answer. Proof in advertising. Okay, moving on. So this is the story of you applied it at the wrong time, it didn't help. But I'm a control theorist, and so for me, the natural question is, all right, what's the best way to structure the drug therapy so that you can get the patient to recover with spending the least amount of drugs and while spending the least amount of time. And so, and this is the part in which I will be rushing through and not providing technical details, even though I do have them. But roughly, we are projecting this three-dimensional system to 2 dimensions using the fact that all of those x1, x2, x3 add up to 1. We have equations for their evolution. There is a control parameter t of t. That's the amount of drugs you are given per unit time. If you do not, the process terminates once GLY either becomes very high, close to 1, there is a failure barrier, or when GLY becomes very low, and this is recovery barrier. So you declare victory here when the trajectory hits here, and you failed if it hits this. If you are not applying any drugs in this region, so whenever it's blue, I'm not using any drugs. Whenever it's yellow, I'm using the maximum tolerable dose, the maximum T which I'm allowed to use. So here I'm just showing you uncontrolled dynamics, and this is the stupidest possible control, just hit the patient with drugs as much as possible all the time. Leads to recovery, but with a lot of drugs. The question is, can we get there with a smaller amount and a smaller amount of drugs? So we introduced the total treatment time. This is the time until you cross one of those 2 barriers, either recovery or failure. And the terminal cost which we imposed is either plus infinity if you failed or 0 if you succeeded. In the process, however, you're paying the integrated cost, which is the drugs per unit time, plus a small constant, which is the cost of time passing. So this is a composite cost, drugs and time. Depending on how I select sigma, I will have different notion of optimality. Once you define this, the value function is the infimum of costs over all possible drug therapy policies, starting with the tumor composition Q0, B0. There is a Hamilton-Jacobi-Bellman PDE coming from dynamic programming, which tells me what is the equation which such a function U, giving you the minimum cost to pay if you're infinitely smart, what is the equation which that U has to satisfy? And what we've done with Mark was we solved it numerically with the boundary conditions corresponding to success and failure. And we're obtaining the control in feedback form. Given the current composition of the tumor, should you be using drugs or not? Based on the structure of the control problem, from this equation, it also falls out that the optimal control will be band-band. That means that you will either not use drugs at all or use the maximum amount you're allowed. So the next slide encodes the optimal policy. Whenever you enter the yellow region, you should be using drugs. Whenever you're in the blue region, you shouldn't be using drugs. And this is an optimal trajectory based on this computation. Is this a clear? That was fun. Interestingly, there are other regimes of parameters in which even if you use the drugs all the time, they are not strong enough to drive you towards recovery. So you have cyclic behavior whether or not you are not using drugs or whether or not you're using them. On the other hand, not all hope is lost. Because if you are smart about combining them and switching from one to another, you actually can drive the system to recovery. And this is the optimal way of doing that, which we can do. Okay. And let me talk a little bit about what we are doing right now with Mingy. Oh, sorry, Bobby, yes.
Can you just explain a little bit more? There's 2 drugs on this slide?
There is one drug only. No drugs are used here at all, on the left. So this is the natural, undriven dynamics of the cancer computation. And here there are drugs used, but the parameter values, benefit of acidification, benefit of vasculature, etc., are such that the drugs don't help you as much. And you cannot quite get to this recovery barrier as a result. 1 second, Bobby, did I?
Yes, that is.
Okay. And so if instead of hitting it all the time, you alternate between the two, you actually can get to the target. Yes, please.
And what's happening at the top, is it like saying, like, I am going to take them to the edge of death? And then...
Yeah, I had a little bit of it even here. You see this enlarged thing? So first of all, it's yellow across along the entire edge here. Otherwise, the arrows would be pointing in the opposite direction. So this entire edge is yellow, even though you cannot see it. And here is the enlarged portion of the tip. So here, nope, you're not going to cross. I'm going to prevent this. But on the other hand, at this point, the natural dynamics without drugs will take you away already, so I'm going to take off my hands. Okay? Sure.
So I assume you have to resolve the PD anytime you change the parameter values?
Yes.
Do you have to resolve it anytime you change the initial conditions?
No, and that's the beauty, thank you so much for this question. This is the beauty of dynamic programming and Hamilton-Jacobi equations. We get the answer in feedback form. So given where you are, what you should be doing. And moreover, it's guaranteed to be globally optimal. And I know that some students might have seen control theory in the context of Pantelian maximum principle, far more popular in engineering. That one is cheaper to compute, but it gives you a necessary condition for local optimality. And every time you are switching initial conditions, you need to resolve the problem. And you're not quite sure whether or not it's a globally optimal thing. In the paper, we have an example where Pantelian maximum principle gives the wrong answer. So no, you're getting the answer for all starting positions at once. Okay? All right. Sorry, Mindy, I will have to make it brief, but I will do my best. So now the stochastic perturbation in fitness of cancer cell types. First of all, there are different types of stochasticity. There is demographic stochasticity, and that is different cells of the same type in the exactly same conditions would be slightly different and would have different fitness and would be dividing at different rates. That's not what we're after here, because that in large populations of cells does not matter that much. Then there is something called environmental stochasticity. This is something which impacts all of the cells of that type right now. And it could be a random event, not related, extrinsic event, not related to the internal logic of the computation. For example, the patient's temperature changes or diet changes. And that somehow impacts the computation for that day. So here is the story of uncontrolled dynamics in the deterministic case. If the fitness functions of the three subtypes are subject to perturbations, random perturbations, this is the trajectory you get instead. And this is the trajectories of the individual subtypes which correspond to this. So one thing to notice is that you are drifting towards the center, for example, in here, even though the control is exactly the same, right? Okay, so the next question is, what if we take what was our optimal policy in the deterministic case, and here is the trajectory which would be optimal in the deterministic case based on the deterministic optimal policy. And we are going to apply that same policy, but in the situation where there are random perturbations to the dynamics due to the changes, stochastic changes in the fitnesses. Then you have this curve. Obviously, every time I would start with the same initial condition, I would have a different curve, and then you have a different cost by the time of recovery. Some of them will never recover. I might cross the failure barrier due to that sequence of random events and the patient dies. But even if I look at only the cases where I do recover, there would be a dramatic spread in possible total costs to recovery incurred up until recovery, along all of those trajectories starting from exactly the same point. In fact, you can look at the CDF shown here in blue. So this is cumulative distribution function for that deterministically optimal policy. Okay, and it shows you that there is quite a spread in possible values, right? So the vertical axis here is the probability of success, and the horizontal axis is of finishing under that amount of total cost. In the work with Mingi Wang and joined with Jake Scott, we're looking for policies which maximize the probability of desirable outcomes, where the desirable outcome would be finishing with total cost under this threshold value, let's say of 4.5. The green curve you see here is the CDF for this threshold aware policy, which maximizes the probability of desirable outcome. You give me a different outcome which is desirable, let's say finishing with the threshold of 4.94, I will produce a different optimal policy which maximizes the probability of that. Each one of them will have its own CDF. What you should be noticing is that the green dot and red dot, the ones which correspond to the threshold values, they're significantly above the blue curve. That means that they're giving you a better probability of success than what we had before. Yes, Mallory?
How do you choose the threshold?
You choose above my pay grade. This is the data which I get from the oncologist. Maybe there is a maximum amount of drugs after which that model doesn't make any sense whatsoever. One of the reasons why using a lot of drugs is bad is, of course, side effects. We all know what horrible side effects the chemotherapy can have. But on the other hand, after a certain amount of time of using drugs, there is resistance evolving among the cancer cells. And so there is a natural limit of how much you can use. Now, to model the waters, this is the threshold for the cost, which involves both time and the drugs. But I'll sweep this one under the rug. Okay, I'll point out that our method, which I wouldn't have time to illustrate in detail, produces the optimal policies for all thresholds at once. So I don't have to resolve it for you, even though the policies are different and have different CDFs. Our method makes the budget, the amount you have left to spend, another dimension in your state space. And so we're solving a PDE, Hamilton-Jacobi PDE, over higher dimensional state space. And as a result, we're getting those optimal policies for a range of different thresholds. And you can look at the results we get and say, maybe I should be using that threshold after the fact. Okay. And this is the order which I probably should skip, so I'm skipping it. This is the Hamilton-Jacobi-Bellman PDE. Those are second-order terms due to the stochastic perturbations present. And this in red are the dependencies of the value function, the minimum you have to spend on the budget S, on that threshold you're trying to meet. That's an extra state variable. Truth and advertising. Do we still have 2 minutes, 1 minute? Yeah. No, before truth and advertising, maybe the better way to spend time is not to give you truth and advertising, because who wants that? And instead to show you a movie. What you see on the right is the value function. V, the minimum you would have to pay starting from each possible position sorry. This is the probability of success, maximized probability of success, starting from each one of those positions with that amount of budget. That will be changing as I showed you. That will be decreasing. And starting with budget 6, and it will be going down. What you see on the left is the map of where you should and shouldn't be using drugs. Yellow means use drugs, blue says don't. Now, that map on the left will be changing as we are already using drugs and as our budget decreases. So, let me play the movie. You can see that the value function here is close to 1, so we started with such a high budget that we could drive the system to cure under that budget with probability close to 1. And now here, starting from here, it would be hard already, the probability of success even when maximized is lower. And you see weird topological changes which we do not know how to explain. Everybody always asks, I don't have a good question, to the region where you should be using drugs as the function of the decreasing budget which you have now. Okay. All right. So the picture is not as interesting from here on, so let me switch to proof and advertising. There are plenty of ways to poke holes in this story. This is a qualitative model. It's not something you can use to treat people. Absolutely. Some of the simplifying assumptions which are not realistic are, we assume that we have full certainty of those parameters. We assume that we can continuously change the drug dose. That's not done in reality. We assume that we can constantly know the state of the tumor. What are you going to do? Do biopsy all the time? No, not really. You need to switch to partially observable control process, and the computational side becomes much, much more expensive. We'll have some proxy, which you can measure in the patient non-invasively. And figuring out what's optimal becomes much harder. We declare our victory or defeat simply based on those X sub i's. How frequent are different subtypes? But I never talked about the actual size of the tumor. That would be based on Z sub i's. That one is not that hard to fix, but we would have a higher dimensional state space and computations become more expensive. We are not modeling mutations or spatial structure. And so it would be interesting to address all of this in the future. But what we have is already relevant enough for identifying the types of issues that people should be thinking of when they're designing protocols for the future clinical trials of interventions. Okay, the conclusions. Evolutionary game theory is fun, provides good qualitative models, and also useful as a foundation for building more believable quantitative models, more detailed. And when coupled with dynamic programming, it might be useful for a variety of areas, including not just adaptive drug therapies, but social engineering. Thanks for your attention. And I know listening on Friday afternoon is hard, so I really appreciate it. Thank you.
have about 3 minutes for questions before we hit the.
Yeah, so let me know if I'm off the mark here, but when you mentioned those 3 types of cancer cells, some of them behave in a manner that might be beneficial for the other cells, and some behave in a manner where it's more neutral, and some behave in a manner where it doesn't necessarily matter what's going on. But from biology's perspective, and again, let me know if I'm off the mark, cancer cells care a lot about proliferation. So I can imagine that even though they have these different dynamics interacting with one another, it doesn't seem like there are existing studies that show that cancer cells can actually end up fighting one another and eradicating the other. So my question is, would that, assuming that this is the case, would that actually change what's going on here as you start qualitatively studying the different interactions between these cells?
So I don't think they're physically eradicating each other. It's just that they're competing for resources, right? And some of them are dividing at a higher rate than the others, and proliferating at a higher rate. And that's what drives the changes in exabytes. So, and even though I don't think there is experimental evidence for this particular story, there is experimental evidence that they do impact each other's proliferation rates very much. And so what's the relative abundance of other types of cancer cells will drive the fitness of each one of the others. Yeah.
And sorry, quick follow-up, and I can imagine this is speaking out loud. I can imagine that if you do have a good handle on that, then you can say, I actually want these GLY cells to proliferate more because the outcome of that would be less severe than the outcome of these other types of cells proliferation. But I don't know anything about.
Yeah. So here, for example, the blue got what I call the well-timed treatment and success.
Right.
That's the case where the defectors got to be the majority of the population. Is it a good thing? Is it a bad thing? I don't know. I was told that my goal is to get rid of GLY.
Yeah.
But when I asked this question of the actual oncologist, he says that maybe we have A, GLY might be more dangerous, and B, maybe we have other ways of treating the cells once GLY are no longer a problem. But in general, people do a lot of work in trying to alternate different types of drug therapies in order to optimally when you switch from one to the other, precisely because you don't want resistance arising, and they are affecting different subtypes of cells to different degrees.
Given the uncertainties in your modeling and so forth, maybe just the takeaway from this is wait until the GLY cells are in a sort of a declining phase and then edit with the drugs? Is that a sufficient rule to?
Yeah, and that's what, look, this is what he did.
Yeah.
Right? So we measured the cost of this, the total cost associated with his empirically found timing. And by the way, it's cheating. As far as I understand, they did try a number of different types and selected the one which gave them the steepest decline and the best result. So we still found a significant improvement on top of that one in that paper with Mark, but it was not huge compared to what they found here empirically.
Yeah, but that's the basic summary of your treatment map, is that
Well,
the yellow one is just like when it's in the declining phase, hit it with a drug.
Yeah, but there are a lot of things happening in here which are more complicated than that. And particularly when I go to this case, where I'm told, well, first don't treat, then treat once you hit this, stop treatment here, let the natural dynamics take you here, and now treat to drive it over. So this is the case where you need several episodes of treatment. And the level at which you are, the level of GLY at which you started to treat here is very different from the level of GLY here. So
Yeah.
I don't think it's reducible to just that, but I think your point is, since you don't know whether or not you can trust that model all that much, maybe you should be just looking for some proxy which is well correlated with the level of GLY, wait for it to decrease, and then hit it. Is a heuristic approach, maybe that's good. I know that there was one clinical study, so there is an interesting story with all this stuff. People were looking for ways to decrease the total amount of drugs for a long time, instead of hitting the patient with maximum tolerable doses. And metronomic policies was the answer for a while. Metronomic means you turn it on, you turn it off at different frequencies. And there were several clinical studies of that, and they were all unsuccessful, very dispiriting. Because it turns out it matters not only how often you turn it on and turn it off, but also when, in what state the whole thing is. And there was one study that I'm aware of with, I think, prostatic cancer, with very small number of participants, but with a pretty dramatic improvement in their life expectancy as a result, which really got a lot of excitement in the field, and a lot of oncologists started to look at this because of that. And there they used the proxy, because they cannot do biopsies all the time. And based on that proxy, they came up with the policy on when to turn on and when to turn off. Yeah. So that's the best I can do based on this.
So, given time, let's take further questions offline. Let's thank Alex again.